Are you ready for searching with the quantum computer? You better brace yourself, because this is not going to be as easy as I thought. So let's get started with a diagram to show how overwhelming this is. Now, in that last video, I mentioned 1024 spots and a phone book and all this stuff. Well, let's see what kind of quantum circuits are involved in making that happen. The search we're performing is called a Grover search. And the Grover search has a certain number of qubits. Now, we had mentioned 10 qubits for 10,024, or not 10,024, 1,024, and that would mean those would have to go through what's called a Hadamard gate, and it would have to be a tensor product of a Hadamard gate over 10 qubits. So those 10 qubits would have to fit in here in our Grover search algorithm, and that would be a 10 by 10 matrix. Notice that it says O. O stands for oracle. Oracle is our search word that we're using here, and it shows the square root of n. So that square root of n would be 1024, and that gives us 32, or in the last video that we pointed out, that ended up being 25. So a lot of wording here and not much substance. So what are these G things here? These G's are the Grover searches that you're continuing to search until you get close enough that you can actually measure. Now notice these other bits coming in here. These other bits are helper bits, and in our example that we're doing in this video is much more simplified than this. Here's within this Grover box is an oracle which tries to select the desired spot that we're going after. It tests it to see if it matches the condition, and then we go and do a phase shift which changes the amplitude, and then we finally head it out here to the measurement. Does that make sense? I don't know if it does, but I'm going to back off and take a 2-qubit search. A 2-qubit search would only involve 4 elements. And those 4 elements are only going to be involved, and you'll say, so what if you get it in one shot? But getting it in one shot proves the idea. So are quantum computers ready to do big searches? No. They're not. All we're doing is proving that the search algorithms will be far superior in an unsorted list. So let me move on to another picture. Here's a picture of our 2-qubit space. Now this makes life a lot simpler. And if we look up here, we have some weird looking symbols. Each one of these represents a 0 state. Each one of these dots represents a 1 spot. So if we look at this particular gate, it says invert this bit down here when both of these are zeros. Invert this bit down here when this one is 0 and this one is 1. Invert this bit down here when we've got 1, 0. And finally, invert this symbol when both of these are 1s. And this is the case that I'm going to to go after. I'm going to show that this particular case, even though it's a, quote, random search, we can actually find this case in one shot, whereas in a classical computer it would take a little bit over 2 searches. Statistically, a little bit over 2 searches to get it, and we'll get it in one search exactly. Seems like a lot to go through, and you'll have to put your seatbelts on because this gets a lot of messy computations that have to go on here. Anyway, this oracle that's represented here, notice we've got 3 lines in and 3 lines out. Those 3 lines in and 3 lines out match up with each one of these ideas. Each one of these is a possible selection choice. And this particular one, 1, 1, is what we're going to choose. I choose that because that is the classical Toffoli gate. What's coming in to each one of these Hadamard gates? And what the heck is a Hadamard gate? A Hadamard gate puts something in superposition. Each one of these is going to be fed with a 0 classical state, which is a 1, 0, 1 over 0, 1 over 0 vector, and this one is going to be fed with a 0 over 1 vector, which is the classical, not classical, but quantum 1 going in here. Each one of these would create a superposition. Why do we need a superposition? Superposition allows the oracle to decide on the sorting process by looking at all the possible states of 2 bits. That means 0, 1, 1, 0, 1, 1, 1, 0. All those different spots are going to be considered by the oracle. What's all this stuff then? If we're searching for it and we identify the search pattern, what's all this for? All of this is so that we can identify it in a measurable quantity out here at the very end. And it's going to take us many steps to get to this point. Let me start with the input to the oracle. The input to the oracle had 3 Hadamard gate outputs. And we have to figure out what a Hadamard gate is. But the 3 inputs to the Hadamard gates were a 0 qubit, 0 qubit, and a 1 qubit. So to establish the superposition, I start with 2 0 qubits for our 2 qubit search. So here's our input column vector. Input column vector is made of these little X's inside the circles are what's called a tensor product, and this plus is the output of taking the superposition or sending it through a Hadamard gate with a 0 qubit, and this is the output that you get from a Hadamard gate when you use a 1 qubit. So we're ready to do some linear algebra. This tensor product ket vector, which is going to be an 8-dimensional vector, will be operated on by a Toffoli matrix. And that will be specially conditioned for the state of 1, 1, which I mentioned earlier. All right, how do you like my chicken tracks here? Anyway, here you see qubit 0 and qubit 1, and those are represented by vectors 1 over 0 and 0 over 1. Now, if we take the Hadamard gate, the Hadamard gate is defined as 1 over square root of 2 times the matrix 1, 1, 1, minus 1. And you see I have a Hadamard gate by a 0 and a 1. If If you remember back to what I said, we're going to be feeding the oracle with superpositions. So we have to create those superpositions. 1 over square root of 2, 1, 1 is the result. Now how do we get that? Well, you take the row times the column. So 1 times 1 is 1, 1 times 0 is 0, that gives us a 1. You take the this one, 1 times 1 is 1, times negative 1 times 0, that gives us a 1 there. Same process is used here, but now we have a 1 qubit, and that comes up to be 1, negative 1. This now gives us the results of, if you break this out into 1, 0 over 0, 1, that gives you a 0, 0 qubit plus 1 qubit, 0 qubit minus 1 qubit. And those can be abbreviated by just using this plus sign and the minus sign. Okay, I've been busy here, and what I want to show you is that we can take these plus superposition and minus superposition. These just mean a superposition when we started with the 0 qubit, superposition when we started with the 1 qubit, and I take those and create a tensor product or an 8-dimensional vector. Here's the steps, and here's the result that I get. Here's a Toffoli gate that flips the bit, and I've got it circled down here where it's just like the identity. There's a nice diagonal of 1s, except right here at the very bottom, things get flipped around. So here's the state that I come up with, and here's the result of that bit flip that occurs. And I've got them all in vector notation down here. So I hope you can follow that along. When we factor out the ancilla bit, we notice that we get, here's the state before we applied the Toffoli gate, and here's the state after we apply the Toffoli gate. And notice it puts a minus sign or marker right on the state that we want to be searching for. Now, once we've done this Toffoli gate, the next step is to do a diffuser operator. Now, what I want to point out is we've already done the search. The search is already done with just one gate over all the possible superpositions that could be there. So now what we want to do is set this thing up finally so that it will allow us to pull out that magic information and of the searched item. The diffuser operator is this scary looking thing, and what we see here is a outer product of the state vectors, and then minus I, which is the identity operator. So let's see if we can build this thing up from scratch. This is the diffuser gate, which handles the inputs after the oracle does the search. Just a couple zeros in superposition, a couple plus gates. And let's see what we got here. We put 2 of them, the outer product, so see if you can make sense of that. Here's a 1/2, here's a 1/2. Here we take a column vector and a row vector, and we just get, wow, big excitement, bunch of 1s. Then once we take this 2, now this 1/4 is because we have 1/2 and 1/2. That gives us 1/4. We multiply all of this by 2, and that gives us 1/2. 2 times 1/4, 1/2. Here's this piece of it. Now we need to subtract the identity gate. Here's the identity gate, and we have to keep in mind this is 1/2 times all of these 1s. So when we do the subtraction, that's going to be 1/2 minus 1 gives us a minus 1/2. So we have a minus 1/2 on each of these columns, and the rest of them just all remain the same, 1/2. Now we apply all this stuff to our state. This is what comes out of the oracle. And we've factored out the ancilla and see it flip state there of that code. Then we take this diffuser gate and multiply or operate on this vector that we show up here, and we get 1, and that's the exact thing that we wanted.